Let's describe what the complex Fourier series is. But first, zoom out for a second and remember that the Fourier series in general is a method to break apart any periodic waveform, any repeating waveform, into sums of simpler waveforms. And those simpler waveforms may be sines and cosines if you're doing the little a sub n, little b sub n Fourier series, also called rectangular. It could be into sums of cosines with phases if you're doing the big a sub n, phi sub n Fourier synthesis, which is also called polar. And now we're going to be introducing a third. And in this, the synthesis equation, and later on we'll talk about the analysis. Synthesis is breaking it apart. Analysis is reforming the original waveform. The synthesis equation is that any function can be broken down into an infinite summation of little c sub n times e to the j n omega naught t. So in some ways, this looks simpler than what we've been doing before when we always had a DC term. Here there's no DC term. On the other hand, here there's another difference that we're going to start summing from negative infinity as opposed to 0. So if you're to write that out explicitly, you'd have your c sub 0 term when n is 0. And for n is 0, c sub n exists. You're raising e to the 0 term, so that becomes 1. And then for n positive 1, we'll have c sub 1 e to the j omega naught t. So that's like the first harmonic. But what makes the complex Fourier series different is that there's two first harmonic components. The other one occurs for n equals negative 1. This would be c sub negative 1 times e to the minus j omega naught t. So we've got two different first harmonics. And if you add those two up together, you can use Euler's relationship to realize that that is exactly the same as that first harmonic of the other types of Fourier series breakouts. Our second harmonic looks like this. And that's the second harmonic. I'd love to write them all out, but I don't have the space or the time to do it. So I'll summarize by just saying it is that infinite summation. So that's the synthesis equation. That's how to break apart your function into this infinite series. It's mathematically much more tractable than the other two types of Fourier series breakouts because there is no DC term. It's just an infinite sum. The opposite of the synthesis is the analysis. That's how to find what these c sub n components are. And that looks a lot like the other Fourier series terms. You'll take the integral over any period of your function like this. Something to realize is as you're writing this down, don't forget that there's a minus sign up here. This is actually an easier way to do analyses because you do not need to find that DC term. So on one hand, this looks like a more complicated integral term since we're taking integrations of complex functions. There's a couple of shortcuts we can use to make this easier. And since I'm the one making the video, I'm going to name them after myself. And the first is that you want to begin by finding c sub naught. But that's the exact same as little a sub naught, capital A sub naught. It's the same thing as the average value. And you can usually find it just by inspection. It's easy to understand why this is true, because if we set n to 0 here, this whole exponential collapses down to 1, and we're just left with the definition of the average value. The second shortcut, this really isn't a shortcut at all. This just says do the work. Find those c sub n's for n greater than or equal to 1. So you got to find it for n equals 1, n equals 2, n equals 3. Turns out that that's not as bad as it looks like, because instead of taking an integral of a cosine, which gives you sine terms, which are, I think, more difficult to work with, the integral of an exponential is just an exponential. But it gets easier. Once you find your c sub n's for n greater than 1, your c sub negative n terms are the exact same thing as your c sub n terms complex conjugated. So, as an example, if your c sub 1 term is equal to, let's say, 2 at an angle of 30 degrees, then your c sub negative 1 would be its complex conjugate. And that cuts down the number of terms you've got to find by half. All right, that's the mathematics behind it, but what's the intuition? The intuition behind the complex Fourier series is this. That's right, there is none. It's very mathematically elegant, but there's no intuition. The form of the Fourier series that you want to do for intuition is the capital A sub n, phi sub n version. Let's talk about power. If we think of the function f of t as a voltage that's going into a 1 ohm resistor, then the power that resistor is dissipating of the nth harmonic is equal to c sub naught squared if n equals 0. So that's the DC term. And of course, the DC term, if you're putting in V volts, would be the square of V volts, because you'd have V volts across the resistor, you'd have V over the 1 ohm resistor of current going through it, and so the power would be the I times V, which would be V squared. For values of n greater than 0, it would be the magnitude of c sub n squared. Now, compare those with what we did earlier using the polar capital A sub n breakdown. And there, it's A sub naught 0 for that DC term, or it's 1/2 of A sub n squared. There's a difference of 1/2. And as a rough hand-waving explanation, that's because, let's say we're looking at the third harmonic. All of the third harmonic's power is composed of this A sub 3 term, 1/2 A sub 3 squared. But that third harmonic is split when using the complex Fourier series breakout into a C sub 3 and also a C sub minus 3. And so therefore, each of our C components for n positive is only 1/2 of the total signal strength of what it is in our capital A sub n components. Let's next take a look at what this means for Parsifals. So Parsifals is also all talking about total power. Now up here we're talking about power of the nth harmonic, but now we're going to talk about the total power, and we know that the total power is the square, really by definition of what RMS means. It's the RMS squared value. RMS, remember, is the equivalent DC voltage that when put through a resistor will cause the same amount of average power to be dissipated by that resistor as the original waveform. Now the Parsifal's theorem says that if you take the sum of our DC component plus the sum of all the higher order harmonics, so this again is the power in the DC component, and then this is the power in all those AC components. And all of that has to equal the total power in your waveform, which we've talked about for a long time is equal to your square of the function dt. you'll recognize this is the square of our function. If we take its integral and divide by the time period, this is the mean of the square. And so if we took its square root of the mean of the square, the root of the mean of the square, we'd end up with the v root mean square, the VRMS value. So this and this is by definition as the total power, and then this is summing up the individual powers. And that's what Parseval's is saying this integral is equal to this sum.